Student, in the previous class we discussed up to the potential energy of a three charged system. Today we discuss the behavior of conductors in electrostatic field. There are some characteristics we see here regarding the behavior of conductor in the electrostatic field. Number one, the net electric field is zero in the interior of a conductor. How can you explain this? We consider an electric field over here which is directed from left to right. In this electric field, we place a conductor. Whenever we place the conductor in the electric field, the free electron start to move in the opposite direction of electric field. That's why left end of the conductor acquire negative charge and the right end of the conductor acquire positive charge. That's why an internal electric field is set up within the conductor, but the direction opposite to the external electric field. But remember one thing, the magnitude of this external electric field and the internal electric field are same, but as their directions are opposite, the net electric field within the conductor is zero. Secondly, the net charge in the interior of a conductor is zero and any excess charge reside at the surface. Now we consider here this is a conductor. Okay, the charge reside on the surface of conductor which is positive in nature. That's why the electric field is in the outward directions. Okay, now we consider a Gaussian surface near to the outer surface of the conductor. As we know, the electric field within the conductor is zero, so therefore flux enclosed by this Gaussian surface is also zero. So therefore, according to Gauss theorem, phi equal integration over closed surface E vector dot ds equal q by epsilon naught is equal 0. Okay, so therefore q equal epsilon naught into 0, that is 0. So therefore we can say the charge present in the interior of a conductor is always 0. Third, potential is constant within and on the surface of a conductor. How can you prove this? Already we know a relation between the electric field and potential as E equal minus dV by dr. Okay, and we know that the electric field within the conductor is 0. So that's why dV by dr equal 0 or dV equal 0. By the integration process, as dV equal 0, we can get V equal constant. So therefore, electric potential within and on the surface of a conductor is always constant. Next, electric field at any point on the surface of charged conductor is proportional to the surface charge density. How can you prove this? We consider the outer surface of a conductor which is irregular in shape. Okay, at any point on the surface of this conductor we want to determine the electric field, for which we consider a small pillbox type cylindrical Gaussian surface about the point. Okay, of this pillbox cylindrical Gaussian surface, some part within the conductor and some part outside the conductor. Okay, so therefore, as the electric field within the conductor is 0, so therefore flux exist for the Gaussian surface only due to outer cross section of the cylinder. Outer cross section of the cylinder. Here del S represent the cross sectional area of the cylinder. So that's why the flux enclosed by this small pillbox type Gaussian surface is given by phi equal E into del S. E into del S. Okay, which is our equation number 1. Okay, and according to Gauss theorem, the charge enclosed by this pillbox Gaussian surface phi equal q by epsilon naught, where q equal sigma into del S. Okay, where sigma be the surface charge density. Now from equation 1 and 2, we can write E del S is equal sigma del S by epsilon naught. So del S cancel. So E equals sigma by epsilon naught, or E vector equals sigma by epsilon naught into n cap. What is n cap? N cap representing the direction of electric field, which is a unit vector normal to the surface in the outer directions. So therefore from this equation, as epsilon naught is constant, we can write E proportional sigma. E proportional sigma. Therefore we can say the electric field at any point on the surface of a conductor is proportional to its surface charge density. And lastly, the electric field is zero in the cavity of a hollow charged conductor. Okay, so this is a hollow charged conductor and this is the cavity. Within this cavity, remember always electric field 0 and the potential is constant. This is also important for 1 mark short questions. Remember it. Okay, so next we move into the discussion of capacitance of a conductor. So what do you mean by capacitance actually? Capacitance means the ability of a conductor to hold some charge. Wherever a conductor holds some charge, some potential is developed in the conductor. And if we increase the amount of charge, the potential of the conductor is also increases. Therefore, from this discussion, for a conductor, we can write Q proportional V. That is, potential is proportional to the charge. Okay, if we omit this proportionality, there is a proportionality constant C, and this proportionality constant C is known as capacitance of the conductor. Now, the capacitance of a conductor depends on some factors. The factors are: number 1, size of the conductor; number 2, nature of the surrounding medium; and number 3, presence of other conductor in its neighborhood. Okay, clear? So now we have to know about the SI unit of this capacitance. From this expression, we can write C equal Q by V. So therefore SI unit of C means the SI unit of Q by SI unit of V, that is Coulomb per volt, which is equal to Farad actually and denoted by F. In numerical, we observe there will be a unit of millifarad, microfarad and picofarad for the capacitance. That's why 1 millifarad is equal 10 to the power minus 3 farad, 1 microfarad equal 10 to the power minus 6 farad, 1 picofarad is equal 10 to the power minus 12 farad. You have to remember. Okay, and the dimensional formula of capacitance is equal M inverse L to the power minus 2 T to the power 4 A square. Thank you student. You remember all this portion very carefully. Okay, next class we start with the discussion of different types of capacitor. Thank you.